Hello everyone, this is ROHC and you are watching Telecom Notes. If you have not subscribed yet, please subscribe this channel and press the bell icon so that you will get the notification for upcoming videos. So today we are discussing about the LTE protocol. So let's start then. Coming to the first slide, radio protocols architecture. We are having control plane and user plane. And in the control plane you will find the layer 3, that is the RRC, radio resource control. After that we are having the PDCP layer, packet data convergence protocol, then RLC, radio link control, medium access control MAC, that is these three makes the combination of layer 2. And after that we are having the physical layer at the end, that is layer 1. So between the RRC and the PDCP we are having the radio bearers, we are having the SRB in the control plane, and for the user plane we are having the DRB, that is data radio bearer, and SRB means signaling radio bearer. And between the RLC and MAC layer you will find the logical channels. Between MAC and physical layer you will find the transport channels, and after the physical layer you will find the physical channels that used to just map over the RBs. Coming to the NAS, non-access stratum. As you can see, we are having three blocks here: UE, eNode B, and MME. So at the UE end, as you can have a look, that RRC, PDCP, RLC, MAC, physical layer, these are just related to the eNode B, as they are just connected to the same part of the eNode B. While in case of NAS, the NAS data is also going through the eNode B, but it can't be decoded by eNode B because it's having the only encoding key that has been just put it by your UE, and after that only MME is having that particular code to just decode that particular message. Coming to the RRC layer functionality, starting from RRC layer, the first one is NAS system information, BCCH, EUTRAN system information, that also just gone through the BCCH channel. Paging will go for the PCCH, paging control channel. RRC connection management, having the temporary ID identifiers, UE, EUTRAN, allocation of signed radio bearer. EUTRAN security, integrity protection for RRC message, management of PTP point-to-point radio bearers, mobility functions, UE measurement reporting control, inter-cell handover, control of cell reselection or selection, UE context transfer between eNode B. The 8th point is MBMS, notification for MBMS services, management of MBMS radio bearers, QoS control, and the last one is transfer of NAS message. Coming to the PDCP layer now, header compression and decompression of IP data flows using the ROHC, robust header compression protocol, transfer of data, that is of user plane and control plane, maintenance of PDCP essence, in sequence delivery of upper layer PDUs, protocol data units, at re-establishment of lower layer, duplicate elimination of lower layer SDUs, that is service data units, at re-establishment of lower layer for radio bearers mapped on RLC acknowledgement mode, ciphering and deciphering of user plane data and control plane data. integrity protection and integrity verification of control plane data only. Time-based discard. Coming to the continuing the PDCP layer functionality now. As you can see at the right hand side, when the data has been just entered in the PDCP layer, first the sequence numbering has been just done over that particular packet. After that, it will go for the header compression only for the user plane data, not for the control plane. For the control plane, at the other end, it will go for the integrity protection. And after that, when the header compression has been just done over user plane and integrity protection has been just done on the control plane, then it will go for the ciphering process, and after that it will put a particular header of the PDCP itself and move on the packet to the next layer. So starting this one, after entering the packet in the PDCP layer, the layer provides the sequence number on the packets. Header compression HC is done over the user plane only, as the user data contains large headers. HC compress the header to 12 bits in DRB, data radio bearers. Integrity protection, the KI is the key for the integrity protection, encodes the data with the key KI, and the control data is decoded by eNodeB and by MME in case of NAS, as we have just seen in the previous slide. Ciphering KC is the key for the ciphering, encodes both planes data and ready to move the packet to the further protocol layer. Before sending the packets to the next protocol layer, RLC, the PDCP puts its header and change the SDU to PDU. The PDU of PDCP layer is the SDU for the RLC layer. That particular formula I'll just tell you afterwards. It's written over here that PDCP PDU is the same for RLC SDU, and PDCP header plus PDCP SDU combined together to make PDCP PDU. Coming to ROHC, robust header compression, it works on three modes. Start with unidirectional mode. From compressor to decompressor, it's one way, no return path for decomp to comp. Bidirectional optimistic mode, you'll find that compressor to decompressor, as well as decompressor is also sending the error recovery requests. While coming for bidirectional reliable mode, compressor will send the data to decompressor, and decompressor also acknowledge for each and every data if it's not having the error also, and if it contains the error, it will send back the ACK or NACK messages for the previous data. More intensive usage of the feedback channel and sticker logic at both the compressor and the decompressor, that prevents loss of context synchronization between the compressor and decompressor. Similar to the unidirectional mode, except that a feedback channel is used to send the error recovery request and optionally acknowledgements of the significant context update from the decompressor to compressor. And it is also having the sparse usage of the feedback channel, having the compression efficiency that makes it the optimistic mode. How ROHC works? ROHC works in three states, starting with the initialization and refresh state. Having the compressor has just been created or reset, full packet headers are sent. Then coming to first order state, detected and stored static fields such as IP address and port number, sending dynamic fields difference, compressing all static fields and most dynamic fields, And after that, second order state, suppressing all dynamic fields such as RTP sequence numbers, and send only the logical sequence number and partial checksum. Other end, regenerate the headers and verifies the header, compressing all static and dynamic fields. Coming to the RLC layer functionality, transfer of upper layer PDUs, error correction through ARQ only for the acknowledgement mode, data transfer, concatenation, segmentation and reassembly of RLC SDUs, UM and AM, resegmentation of RLC data PDUs for acknowledgement mode only, reordering of RLC data PDUs, that is UM and AM, duplicate detection in case of UM and AM, RLC SDU discard again for the same two modes, RLC re-establishment and error detection and recovery. Coming to the details, the first one is the acknowledgement mode, in which receive from PDCP RLC. After that, add to transmission buffer, then go for segmentation and concatenation, keep a copy for retransmission, add RLC header and pass to the MAC sublayer. So receive the upper layer SDU from PDCP or RRC, add the SDU to the transmit buffer, segment the SDU into RLC PDUs when the MAC scheduler permits transmission, make a copy of the transmit buffer for possible retransmissions, add the RLC header to the RLC PDUs, pass the RLC PDUs to MAC for transmission over the air. Coming to the unacknowledged mode, receive the PDCP RLC, add the transmission buffer, segmentation and concatenation, add RLC header, pass to MAC sublayer. Receive the upper layer SDU from PDCP or RRC, add the SDU to transmit buffer, segment the SDU into RLC PDUs when the MAC scheduler permits transmission, add the RLC header to the RLC PDU, pass the RLC PDUs to MAC for transmission over the air. For the transparent mode, no segmentation and concatenation happens, no RLC headers are added, do not have any guarantee of putting the data, and mostly we use this mode for carrying the voice. Coming to the MAC layer now, mapping between it's written transparent, it's transport and logical channels, error correction through hybrid ARQ, priority handling and dynamic scheduling, logical channels prioritization. As you can see in this image, these are the channels, and all the logical channels: PCCH, BCCH, CCCH, DCCH, DTCH. PCCH is paging control channel, BCCH is broadcast control channel, CCCH is common control channel, DCCH is dedicated control channel, DTCH is dedicated transfer channel. So as in the image you can have a look that it's having logical channel prioritization for CCCH, DCCH and DTCH. That has been just put it after that it will just put multiplexing and demultiplexing, and at DLSCH you will have a look over the HARQ functional. It seems that PCCH does not get manipulated by MAC in the special way. It just looks as if it's bypass MAC process. It does not use HARQ procedure, meaning no retransmission mechanism being used. CCCH, DCCH, DTCH all go through the same procedure of prioritization, MUX, DMUX, that is multiplexing and demultiplexing, and HARQ. Some BCCH goes through HARQ, but some BCCH do not go through HARQ. Do you know which BCCH go through HARQ and which does not? BCCH for MIB does not go through HARQ process, but BCCH for SIP go through the HARQ process. But this HARQ is a little different from normal HARQ that we know of. It does not expecting any ACK or NAC response from the receiver, but performs retransmission based on the predefined rule. Coming to the protocols configuration example, that is the example we have just taken. At the left hand side we are having the NAS and RRC having the signaling radio bearer. That means it's the control plane. After that the PDCP layer puts the integrity and ciphering over that particular data of coming from the RRC, and by using the KI and KC keys. After it has been just passed to RLC layer having the acknowledgement mode. After that has been just put it over the logical channels. By example we have just taken DCCH, and after that multiple to single mapping has been just done, because in the transport channels we are having downlink shared channel that has been just shared by the multiple logical channels. So it's been just mapped over DLSCH, and single to single mapping between the shared channels, because in the physical channels also we are having the shared channel having PDSCH, physical downlink shared channel. Using at the user data now, we have just taken the example of email and FTP. In email we are having UDP protocol, and in FTP we are having TCP protocol. In both the cases the DRB has been just created, data radio bearer. As we know, integrity is just for the C plane, not for U plane. So in case of user plane you will find ciphering and ROHC, robust header compression. After that it moves to the RLC and you will get the acknowledgement mode. And as you can have a look that in email and FTP we are transferring the data, so it's DTCH channel now. It's not for the control channel, it's the transfer channel. After that it has been just put it for the prioritization process, multiple to single mapping by map. In this we use the MAC scheduler also. After putting to the DLSCH, again it has been just mapped over the physical channel, that is PDSCH. Coming to data flow example, we have taken the example of email and FTP download. As we can have a look, we are having the payload with the header. Then PDCP header compression has been just done. Header has been just converted into simple H, because header compression has been just done over that one. And after that putting that header compression, that particular packet has been just delivered forward having the PDCP header. After putting the PDCP header now, as you can have a look, we are having the same formula. PDCP SDU plus PDCP header makes PDCP PDU. So right now we are having this, just wait for a second. Yeah, right now we are having this PDCP SDU and PDCP header. So this whole combines and makes PDCP PDU. As you can have a look, this is PDCP PDU. But when it just moves for the RLC one, it's the SDU for RLC, and it's the for PDCP it's PDU. So we can call it PDCP PDU, or we can also call it when it's moved to the RLC that this is RLC SDU. After RLC SDU, segmentation and concatenation has been just done, as you can see in the FTP download, that it's subdivided into two parts. It's been just concatenated. After that, RLC header has been just put it. Now RLC header and RLC SDU will make RLC PDU, and when it just moves up at the MAC, you can have a look that they are just combined by using the process of prioritization and multiplexing. It creates RLC PDU here, and after putting the MAC header, it again creates RLC PDU is MAC SDU, and MAC header will combinedly called as MAC PDU now. MAC PDU has been just transferred over the physical channel. In the physical channel, it will be treated like a transparent block, and we will put 24 bits of cyclic redundancy check. So that's all from my side for today, and thank you for watching the video. Stay connected, guys.